let me introduce Mark. So Mark Vogelsberger, he is from MIT now, and he is a great, if not the greatest expert in numerical simulations nowadays, the most comprehensive, the most advanced, the most successful, I should say. So he's been the lead person on the Illustris simulation, and also he is keep doing this with the IllustrisTNG, the next generation simulations of the universe, the structure formation, the galaxy formation, and all related issues. He originally is from Germany. He got his PhD with Simon White at Max Planck Institute, and he also was at Munich University, as far as I remember, right? He got the Kippenheim Award for the thesis, for his thesis, and then moved to the US. As a postdoc, he was the ITC fellow at the Center for Astrophysics at Harvard. And in a few years, he became a Hubble fellow and stayed there. Then in 2014, he moved to MIT, just across the city of Cambridge. He got the assistant professor position. In 2 years, he was awarded the Alfred Sloan Foundation Award, his fellowship. And then, as far as I know now, you're an associate professor already just 4 years after. He's already been put up in that stair. So today I believe we're going to hear some results that you've done in the past years in simulating the universe. So if somebody is interested in going to dinner with the speaker, we're going to gather together and decide where we go just after the colloquium. So now floor is yours.
Thanks a lot, Misha. Thanks a lot for this. Thanks a lot for this nice intro, although it might have been a bit exaggerated to the positive sense. Yeah, it's great to be here. It's my first visit here. I'm really glad that you invited me. It's really a pleasure to be here. And I had a lot of great meetings with various people here, with the students, faculty, postdocs. It's really great. Yeah, so as Misha said, I will talk about galaxy formation simulations. So that became a huge field over the last 10, 15 years. So there's a lot of groups working on, various simulations of galaxy formation, different aspects of it. So what I will try in this talk, I try to give you first a bit of an overview what we do with these simulations, and then tell you where we currently stand with the simulations, and then try to give as honest as possible overview what the limitations are, and then tell you where we might go over the next maybe 5 years with these simulations. So before I start, I just want to briefly emphasize what we actually want to do with these simulations. I guess maybe all of you know this already, but just to set the stage. So what we try to do is we try to simulate the formation of galaxies, and we know observationally from many galaxy surveys, from observations with telescopes and satellites and so on, that there are different types of galaxies and they change as a function of time and so on and so forth. And you see here a typical, kind of a Hubble fog diagram of some galaxies like spiral galaxies and elliptical galaxies. You can already by eye see that they are different, right? So some are more bluish, some are more red, some have different shapes and so on and so forth. The question is, can we understand this with a simulation? So that's with a model that we incorporate into a simulation code, put it on the computer and create a kind of virtual universe. And the question then is, does this virtual universe agree with our universe? And if so, we can then learn about various physical mechanisms that play a role for galaxy formation. So that's the goal. And the framework within which we simulate all this, or within which we develop the models, is the standard, Big Bang model with the inflationary phase. So we have some initial conditions, and you evolve those forward using some equations of physics. And our simulations specifically are initialized with input from the CMB. We do not start here at the Big Bang, but we typically start simulations at a redshift of 100 or 200. So we take the input from the CMB, then we do linear perturbation theory up to a redshift of 100. and then this input goes into the simulation, and then since structural formation then slowly becomes nonlinear, then the computer takes over and simulates the rest, which is of course a huge time span, because at the end of the day we want to evolve this all to the present day redshift 0, so 13.8 billion years after the Big Bang. Then if you do galaxy formation, there are different phases of galaxy formation. So the first galaxies are supposed to form around a time of 1 billion years after the Big Bang. There are specific simulations that look at the formation of the first galaxies. So what I will talk about is not this early type of galaxy. I talk more about these late type galaxies. Also, I will not talk about the first stars. That's also a different set of simulations where you need different physics partially and also more resolution. So there are special groups working more on this, so I will more talk about this late time evolution, with the goal of comparing our results to real observational data. Yeah, so problem, for example, is if you do POP3 star formation, we don't have any observational constraints, at least no direct constraints. So that is different in the late universe, where we can really compare to data, and that's a very important step in the whole process. Now, the problem of galaxy formation can be summarized in one slide, kind of. So what you see here is, on the left is actually a plot which shows you two things. So this colored line here shows you the kind of schematically a halo mass function over a certain dynamic range. So what this means, it shows you number density of dark matter halos as a function of their mass. And the black line shows you here the corresponding stellar mass function. And so what you see here is that the two functions are not just scaled versions of each other. So that means if I have dark matter halos, which build the backbone of structure formation, as you can see here, so this is a typical dark matter density field, you cannot just simply put, certain fractions of that halo mass into this halo and turn it into stellar mass. That's not going to work, so the process is more complicated. And what we think what is needed to turn this halo mass function into a stellar mass function, to also into the galaxy population. So what's needed for that are some kind of feedback processes. So that's always a weird term if simulators talk about feedback. So what that means simply is that if you have, for example, supernova going off as part of stellar evolution, they will inject a certain amount of energy and momentum into the interstellar medium, and that will prevent to some degree the formation of new stars, because new stars can only form out of quite cold gas. Yeah, so there's a natural feedback loop. If you create stars, they will cause supernova, and that will then prevent the formation of stars. So there's a self-regulation going on. So we believe that this is an important mechanism here. Then at the massive end, supernova feedback is typically not strong enough to prevent star formation. So what we need there, or what we believe what is needed there, is the feedback related to supermassive black hole. What is an AGN feedback? Yeah. And these two processes are needed to turn this colored line into the black line. So the whole talk and the whole field of galaxy formation, and every aspect or most of the aspects of galaxy formation, are actually related to the central question: how do you turn this colored line into the black line? Yeah, that's the problem. And at the end of the day, what you want is then you want to have a predictive theory of galaxy formation. Yeah, that means you do not want to only describe the observations, but you also want to make predictions. And ideally, although this is never really strongly articulated in all of the papers and all of our talks and all of our work, is that ideally you want the model to fail. I know this is not a very popular point of view, but we can only make progress if the model fails. If we have only models that describe everything, then we will not understand anything better. So the key ingredient is that you have a model that fails to some degree. And this is why it's important that you make specific predictions also. So how do you do this? Well, there's a couple of key ingredients that you need. Obviously, you want to model in these simulations the dark matter component, the baryonic component, and the dark energy. So all this has to be included. And it's very important to model the baryons, because without any baryons, we cannot easily connect to observations. So we can very easily run very large dark matter only simulations, but then it's very difficult to connect to actual observations. So we really want to model the baryons. That means that you also have to include a certain range of physical processes, and what these processes are, we'll come back to that in a few minutes. It's, for example, these feedback processes you want to include. And at the same time, you also want to have as accurate as possible and as efficient as possible numerical schemes, so that you can run large simulations and minimize numerical errors. Because at the end of the day, these are all numerical calculations. There are, these are schemes of a certain order, so they have errors, and we want to minimize all these errors. And we want the simulations also to run fast. And if you have all this, then you also want to make sure that you simulate a statistically significant sample. It's especially important if you want to compare to surveys, large surveys, SDSS, LSST, or whatever might be around. You really want to have a large volume. And you want to have this large volume simulated with a high numerical resolution to resolve also the details of the galaxy. And in the last step, once you have all that, you finally also want to construct mock observations. So that became very popular over the last couple of years. So we typically in the simulation community, we can very easily predict, for example, the stellar mass of a galaxy. But then for an observer, this is a highly non-trivial task to derive a stellar mass from a galaxy. So what we typically do now is we try to make mock observations that the observers can then use to run through their same pipeline to make a more even-handed comparison. Of course, there are also a lot of caveats in this construction of the mock observations, but that became more popular over the last couple of years to compare essentially with observational data. So that's the whole program that we typically do in galaxy formation simulations. Now, if you do these simulations, there are generally two approaches how you can do it. There's the so-called bottom-up and top-down approach. So what's the difference? Well, for the bottom-up, you say you simulate a small system, and by small, I mean small in terms of galactic scales. So, for example, an individual galaxy, as you can see it here, and you put all your computational power on this small galaxy. This has the advantage that you can model a lot of details in the galaxy, but the problem is you are limited in terms of the statistics. You just have a handful or 10 galaxies that you can afford to simulate. You don't have a lot of statistics. The other approach is a top-down approach where you simulate a large volume, something like 100 megaparsec cube, a large patch of the universe. Then you get a lot of galaxies there, but you have to live with some approximations for the physics of these galaxies. So if you write this down in pros and cons, this is what I just said. And of course, also these simulations have to live with some approximations, because even on these scales, you cannot model the formation of individual stars. But the scale where the approximation sets in is just a different one for this one compared to that one. All these simulations have to rely on effective so-called sub-resolution models. In none of these simulations, you will be able to form self-consistently a black hole, or self-consistently model a supernova, or self-consistently form a star. They all rely on sub-resolution models. So independent what people tell you, all of these simulations have to rely on sub-resolution models. That's it's not a caveat, it's just a feature of these simulations. There's no way around it because of the huge dynamic range. Now, one of these simulations was, as Misha already mentioned, this Illustris simulation that we ran or finished in 2014. So this is just a zoom into the matter field at Redshift 0. It started with the dark matter density field, and now you see the gas temperature field. And on the left, you see always the scale. So the whole simulation volume is 100 megaparsec here. And we keep zooming in. Now is the gas metallicity, so the distribution of heavy elements, everything heavier than helium. And then this is eventually the stellar light in these simulations in SDSS composite. And this is a late type galaxy, a bit more heavy than the Milky Way, also a bit larger. But of these galaxies are still resolved with about 500,000 or 1 million resolution elements. You can really look still into the details of these galaxies. And of these galaxies at that resolution level, with that level of detail, there are about 50 or 100,000 in these simulations typically. So you can really do some statistics with them. And as you zoom out, you can also see some features in the gas density here. For example, you see outflows, which are also modeled, and you can see a lot of other gas effects like ram pressure stripping and many other things if you would look here in more high density environments. And then eventually the movie shows the velocity here. You see this high velocity of the gas that is realizing in more massive halos, and then the movie will switch back to the dark matter density field. So this is what we could do 2014-15 approximately. And you can then also summarize these simulations on a kind of Moore's law plot. So if you plot the time on the x-axis and then the number of resolution elements, which is kind of the key ingredient of these simulations in terms of how well you can resolve the details, you can see here two lines. One is the dashed line. This is the typical n-body line. So these are simulations which only model the dark matter component, like the Millennium simulation or the Bolshoi simulations or many of these other dark matter only simulations. And you can see this line is growing exponentially. And in fact, today, since a couple of years, it's possible to run multi-trillion particle simulations, dark matter only. And if you look back in the 70s, typical simulations had a few 10,000 or a few thousand particles, so it really grew dramatically. You see the same trend for the solid line, which are the hydrodynamic simulations. These are simulations which also include the baryons. It's also exponentially growing, and you see this clustering of simulations here at around 2014 and 15. So a lot of simulations, a lot of group actually put out these large hydro simulations around that time when also the Illustris simulation came out. And in fact, if you continue that plot now, if you put IllustrisTNG, which is this new version of Illustris, also on the same line, you also see that it's again larger. Again, simulators like to show this plot a lot. However, I should say that the number of resolution elements does not necessarily scale with the quality or amount of science that you get out of these simulations. So in fact, if you look at the simulations in the 70s or 80s, they had very low resolution, but people could still already there do great science with the simulations, right? So it's just an indicator on how much bigger the machines got and how much better the algorithms got. Yeah. Of course, you can now look into more details, but it doesn't necessarily mean that you can also do a lot of science with significantly smaller simulations, even today. Okay, so now what goes in these simulations in terms of the physics? So I mentioned some physical processes have to go into the baryon sector to make this whole thing work, and this is kind of a rather high-level list of what has to go into, or what's going into the Illustris model, which is kind of the same what's also going in some of the other simulations. So first of all, simulations have to model hydrodynamics, which is just the model for the gas that you have. If you start with a helium-hydrogen mixture, you model this just essentially through the Euler equations. And then you have to have a couple of other processes. You have to include then metalline cooling and primordial cooling. These are all atomic cooling processes. You include also some form of radiation, which is a UV radiation, and then you have to have a model for star formation. And then most importantly, these feedback processes, which are related to supernova and to supermassive black holes. So you have to all include this. So in fact, if you remove one of those, the galaxy population that you will get would already look rather different and would not agree with many of the observational constraints, essentially. So this is kind of what was figured out over the last 10, 20 years, that this is the minimum set of physics that you have to put in to get a realistic galaxy population. And that's also the basis of the galaxy formation models, both in Illustris and IllustrisTNG. Now, when you run this simulation, you get some galaxies out. So this is just an overview of some Illustris galaxies. So these are star-forming disk galaxies, and these are red and dead elliptical galaxies. I mentioned before that there were other groups that also ran simulations around that time. So this is a compilation of simulations that all finished between 2014 and 17. So there's this Eagle simulation, Horizon AGN simulation, and they all get now a certain level of diversity in the simulated galaxies, which was rather difficult to achieve something like 10 or 15 years ago. So that became only possible over the last couple of years. Now then the question is always, how does that compare to observations? So I will show from time to time now a few comparisons to observations. And one thing that worked very well for Illustris is, and also for these other simulations that came out 2015 or so, is this comparison to, or is this diversity aspect of the galaxies. So what is the mix of galaxies that you get at a given stellar mass? So that's shown here in this plot. On the x-axis, you see the stellar mass of galaxies. On the y-axis, you see the fraction in different types of galaxies, so split here in early type and late type galaxies. And then these blue and red data points, these are observational points, and the solid line is the simulation prediction. Now, since this is a physics department, and since there are a lot of physicists here, for high energy standards, that looks probably very, very bad. But for astrophysics standards, this is actually a reasonably good agreement, because the main point here is that we get this trend right. It was very difficult in the simulations before to see at all a proper trend here with stellar mass, such that with increasing stellar mass, you would increase the fraction of early types and decrease the fraction of late types. In fact, in 2010 and 11, it was still not possible to produce a single late type galaxy in a simulation. Which is just 7 years ago. Or 8 years ago. So in that sense, this was was one of the major steps forward in the modeling.
About 2 slides back, you had all the different physics that goes in.
Yeah.
Is that done in a way where there are model parameters in that, or is that all ab initio?
Yeah, I will come back to that later, but yeah, all these simulations, since they have to do, they do this effective sub-resolution modeling, they come with a certain number of free parameters. Yeah. So the way it's done is that these parameters are gauged based on a subset of observables and then set to certain values, and then the rest of the simulation is a prediction. So there's a subset of 3, 4, or 5 observables that the parameters are gauged to, and then everything else is a prediction.
Calibrated.
Yeah, it's calibrated essentially, yeah. Okay, and then last, another thing that I briefly want to mention here, but I mentioned already before, is this aspect of mock observation. So what you see here is something that also became very popular after we did this here, is the construction of these mock observations. So what you see here is two Hubble ultra deep fields. And so one is a real one and one is a simulated one. And so the left one here is from HST, the right one is simulated. And I don't want to go into too much details here, but in fact, if you construct these light cones, and if you look at this in detail statistically, you will actually see that that both of them are very similar, right? We can now, as a function of redshift, even describe the galaxy population very well. Yeah, both the colors, the morphology, and also the stellar masses and so on. Yeah, so that works also very well now. Okay, so that was the old stuff. So then let me come to the more recent material, which is this IllustrisTNG simulation. So the first question is, you might ask, why do we need yet another simulation? Yeah, we just finished the old simulation. And the main reason is that the old simulation had a volume, and also the galaxy formation model was essentially tuned to a volume of around 100 megaparsec cube. So we could not do galaxy clusters, and we could also not do dwarf galaxies. It was just mostly around L-star galaxies that we were interested in. However, we wanted to extend this to smaller and larger scales, and this is where this IllustrisTNG project comes in, which is part of the overall Illustris project and just a follow-up of that. And just for the people who are interested a bit more in the details, how this model building works. So this, for all of those who are not so interested, maybe should not listen for 10 seconds, but just for the people that are interested. So this is kind of a family tree of this Illustris model, yeah, so which is up here. So you can see what all these ingredients that decades of work went into that model, and it was just synthesized in this Illustris model. Yeah, so there were a lot of different layers and a lot of different people who have worked on that. And that was the model that was used then for this Illustris simulation. Now we have this TNG model, or IllustrisTNG model, and the major difference is that we have a new prescription for the AGN feedback that was required for the modeling of clusters. So before we didn't have many clusters in the simulations, and we didn't bother too much about the exact details of the cluster physics. But now we, as I will show in a few seconds, we have a 300 megaparsec volume as well, and there are 400 clusters in that volume. So we also want to model that properly. So it needed to have a revised AGN feedback, essentially. That's something that Rainer Weinberger developed. The rest of the model, there was some minor retuning, but the major change is essentially this AGN feedback. Now with that in mind, and with that change, we then ran 3 boxes. Yeah, so there's which are called TNG 50, 100, and 300, representing the size of the box. So this is a 50 megaparsec cube, 100 megaparsec cube, and 300 megaparsec cube. And all of those have different science goals. Yeah? So there's this small box which is ideal for dwarf scales, then the L-star box, and then something for galaxy clusters. And all this was run with this updated model that I just mentioned. Yeah. And so this box here is still running. That's currently at Redshift 0.27 or so. All the other boxes are already finished. Yeah, and unfortunately, all this is rather expensive. So if you sum up everything with all test simulations and so on, you need somewhere between 2 or 250 million CPU hours. So it's a rather expensive calculation. So in fact, this TNG 50 box is essentially running, or needs to run more than a year constantly on 20,000 cores. I mean, constantly every day. So it's rather expensive, unfortunately. Good. So that is what we have. So again, for the experts, here are some more details about this TNG 300 and 100 box, like particle number and so on and so forth. So this TNG 300 box has now more than 30 billion resolution elements, which is, it's also a quite substantial number of resolution elements. Okay, and then there's another addition to this latest set of simulations, which is shown here. So this is a movie showing actually the time evolution. So Redshift is running here. It shows the time evolution of, or it shows the gas essentially in the box. But it's not showing the gas density or the gas temperature or metallicity. But what you see here color-coded is in fact the field strength, the magnetic field strength in the gas. Yeah, so that's the first simulation which self-consistently also models the magnetic fields. So it solves self-consistently the MHD equations. So that is something that was also not possible before, that we could also not do a couple of years ago. And the nice thing then is you can make then also predictions for the field strength and compare this, for example, to Faraday rotation measurements and see whether also the field amplification is modeled correctly. Yeah.
Why were you even close without the magnetic field before?
Why we were close?
Why were you even anywhere near close to being correct without the magnetic field before? Because magnetic effects are so big.
Well, the fields that you get in a Milky Way-like galaxy of the order of 10 microgauss, right? In clusters, it can be 50. So if you calculate the magnetic pressure, it's typically subdominant for the dynamical evolution of the gas. In the very centers, you can reach equipartition, but it's really a tiny region where this matters. So for most of the galaxy evolution, the magnetic fields are just carried along, but they are dynamically not very important in most cases.
Well, that sounds like a circular statement. So if it didn't change that much, then of course it wasn't too big. How do you know it's not?
Because we can take the same sub-resolution model.
Could you make it fail with a magnetic field?
Yes, if you take extremely large seed fields, which violate Planck constraints, then you can make it fail. If I take a seed field which is 100 times larger than the upper Planck constraint for the initial magnetic seed field, the galaxy formation will work differently in the sense that the galaxy luminosity function will not agree with SDSS measurements anymore. So for all the seed fields that are viable, it's still okay. And in fact, it's also extremely insensitive to the fields because the dynamo grows exponentially, the fields, and so they saturate all to the same value, roughly, unless you go crazy with the initial seed fields. So for those reasonable seed fields, which are within seed constraints, there's no dynamical impact and no impact on the galaxy population of the magnetic fields. Yeah. So in that case, it's kind of a passive tracer to some degree. But it's an interesting passive tracer because we have observations of magnetic fields through Faraday rotation measurements, for example. Yeah. So that is why it's interesting. It's a very good question, but I mean we thought a bit about this, and so most of the tests indicate that's dynamically not important for most of the situations. Okay, so then after this brief intro, let me give you some results that we got from TNG. So this is just a kind of a random collection of results. So I didn't stick to any specific paper here. So there were a couple of papers published recently. There are more now, but there were a few science topics explored in the first set of papers. So depending on what you're interested in, you might want to read some of those papers. Interesting. There's one interesting paper, which is this R process element paper. So that was actually came out before all this hype around R processes started with neutron star mergers. So that's actually kind of interesting because there's a model for neutron star mergers in the simulation to predict R process production. Yeah, so that paper became probably more popular than initially anticipated because of the recent developments. Yeah. Generally, if you're interested in metaclustering, then there's a paper by Volker Springel, and whatever you are interested in, there is hopefully something that might interest you. So let me show some of these results. So the zeroth order test you can do with your galaxy formation model is actually to make sure that the clustering of galaxies is correct. And we have very good data on the low redshift clustering through SDSS. And this is what you see here. And the different panels, there are different stellar mass spins shown. And the red line is the simulation prediction. And then the points here is data from SDSS at a redshift of 0.1. And again, the agreement is of course not perfect, but you can see that generally at all these mass spins, this works remarkably well. And in fact, this works as well now as semi-analytic models. So there was not a single hydro simulation where this worked so well before. Should also say that the error bars here on these points are negligible, right? There's no error bars even shown. So of course, the line would still be many sigmas away here, but again, it's mostly about the general trend that we got this right. And again, it's much closer to any previous attempts that we had. So that's the zeroth order test you do, that the clustering of galaxies is correct. But this is just shown here through this 2-point correlation function.
Why do you have 6 graphs when it looks like 6 copies of the same thing?
Because we filter for the stellar mass of the galaxy. So in this case, it's between 10 to the 8.5 and 10 to the 9, and then it just keeps going.
They all look the same. Don't they?
No, the clustering signal is the details are slightly different, but the slope is very similar. Yeah. But you want to test this that the clustering for all galaxy masses works correctly. Right.
If you put everything on one graph, would they all fit pretty much on top of each other?
No, because this goes a bit into the details. So the galaxies, depending on where they live, what their masses are, the clustering is slightly different. I mean, if you would put them all on one graph, also if you would filter by environment, which is another cut you could do, or by color, you would see that the clustering would look a bit different. But if you take the overall galaxy population, it's described reasonably well by this function, just coarsely speaking. Yeah. That's the observational result. I cannot change it. So I'm sorry. Okay, good. So let's continue. Another interesting thing, and that is not related to the clustering, it's related to the colors of galaxies. It's also it's surprisingly difficult to get colors of galaxies right. This sounds like a trivial thing, but if you think about it, maybe it's not so trivial, because to get the color right, you have to get all the stellar populations in the galaxy right. So this is something that was also improved in the new model. So what you see here is, again, for different stellar mass bands. In black, I think it's in black, the SDSS result, and then in blue, this IllustrisTNG result. Again, no perfect agreement, but the main point is that you get this bimodal distribution at the right stellar masses, and that you shift to a more reddish population also at the right stellar mass. So this goes along with the idea of mass quenching, essentially, that you shift more towards these redder galaxies, and that also didn't work very well before. And so that's also something that was difficult to achieve. And another thing, which is now more prediction, not a test with the observations, more prediction of the model, is the following. Once you believe that your galaxy formation model is correct based on all the tests that I just mentioned, you can also make predictions. For example, you can predict how much the total matter power spectrum is changed if you include this baryonic physics. As you might know, people try with weak lensing surveys to constrain cosmology based on the total dark matter density field, or the total matter power spectrum. And the world would be very simple if this total matter power spectrum could just easily predict it with dark matter only simulations. But the problem is, as soon as you include baryons, you change the total matter power spectrum. That's shown in this plot, and we can just focus here on the upper left. What's shown here is the logarithm of the ratio of a full physics simulation, which includes these baryons, divided by a simulation which only models the dark matter component. So in an ideal world, this should be 1, this ratio, so the logarithm should be 0. However, you see these features, and those are all related to these energetic feedback processes and the reshuffling and the cooling and star formation of the baryonic component. So it's unfortunately more complicated to understand the total matter power spectrum, and in fact you have to take these baryonic effects into account. Good. Then let me just show 2 or 3 more results, and then I come to the next part of my talk. So another thing that we just mentioned is we can also simulate now magnetic fields. So this is something that Federico Marinacci has studied a lot. Don't want to go into too many details here, but what you see here is for elliptical galaxies on the left and for spiral galaxies on the right, the topology of the magnetic field. So you can not only predict the strength, but also the topology, and then you can make these, and in fact, some other people are looking now in more detail into this. You can then correlate the topology with the galaxy type. For example, it's more ordered here in these spiral galaxies, and it's more chaotic topology in these elliptical galaxies, which just has to do, of course, with the way how the gas is arranged in these galaxies and how it moves. But there's probably also a lot of interesting things. And again, there was recently a paper where someone of the collaboration looked at, again, Faraday predictions for these kind of galaxies, and you can compare this again to data then to see how realistic your dynamo is working and the magnetic fields are amplified. Another thing you can do once you have magnetic fields, you can also make predictions for radio emission, so synchrotron emission. So these are just some predictions for SKA and so on. And you can then also test correlations. I just want to briefly show this, for example, between X-ray and radio power. You can correlate this, and the gray here is some observational data, and the blue are simulation predictions. And again, the main point is that we are not extremely far away or from the observational data, so the correlation looks kind of, similar, at least in the trend. So that's an additional test that we can do now, which we could not do before, right? You always want to. This is what I meant. You want to have a predictive model such that you can make as many tests as possible. And of course, so far everything I showed, it didn't really dramatically fail. So it's not yet at an interesting point. It just all works so far. And in fact, there were a couple of more papers written about this, and there was so far not a major catastrophe where the model completely failed. Of course, there are small discrepancies here and there, but this major thing that broke hasn't yet been found. And the interesting thing will always be what really breaks, and maybe something at higher redshifts breaks. So these are mostly low redshift results. Yeah. Again, I cannot emphasize this enough. It's the goal to find the point where it breaks, because that is where it gets interesting. Yeah. Okay, and then just the last thing I want to show is also because we have now this large sample of clusters, you can also now study the ICM in great detail in clusters. For example, this is a collection of metal maps in the cluster, actually mostly iron is here in the cluster, how it is distributed, and then you can also study how well this agrees with observational data. So this is shown here. Black, this is a radial profile of metallicity, measured from X-ray service, and then the blue line is what the simulation predicts, the median over the whole sample, essentially, that we have over these 400 clusters. And you can again see that works remarkably well now. And even more, you can also now, there's a distinction in clusters, so-called cool core and non-cool core clusters, and they also show a dichotomy in the metallicity profiles. Also this you can reproduce here. So the data is, unfortunately, the X-ray data is, it's very uncertain, but there's a hint in the X-ray data, which is shown by these blue and red contours here, that cool core clusters have a higher metallicity at the center than non-cool core clusters, and the solid lines here are the simulation prediction, and again, this goes in the right direction. Whether this is quantitatively right, we don't know, because both the simulation and the data don't really have the full statistics to explore this in detail, but at least qualitatively it shows the right direction. Okay, let me skip over that and come to the interesting part. So the question is, was anybody interested? Okay, sorry, I didn't want to. Okay, sorry. Yeah, I thought it's my paper, so I can skip over it. But so what's showing here is actually the redshift evolution of the metallicity, and it is an interesting result. So I apologize that I skipped over it, because it shows essentially, and this is a recent X-ray finding also, that the metallicity of the clusters is remarkably constant beyond a redshift of 1. Right? You measure this, and it's super constant. It's always around 0.3 solar. This is this canonical value. So what you see here is actually a plot of that. It shows the average metallicity within R500 of the full ICM, and this gray line is some observational data from Mike McDonald measured within a certain radius, and then there's from Mans et al. Another data set measured within another radius, and then the solid lines show the simulation prediction. You can see they agree, at least in this trend of being very constant with the observational data here. And we looked at this, and for the details you have to look at this paper. We looked at this in detail where this comes from. Essentially, this is another strong indicator for what's known as the super early pre-enrichment of the protocluster environment. So what happens is you pre-enrich the protocluster environment in the simulation early on, and then only gas with a certain metallicity level falls in. And that sets this constant level. So the cluster still accretes a lot of gas, but the gas has all the same metallicity. For the non-astrophysicists here, so metallicity simply means the fraction of heavy elements in the gas, right? So it's just always the same fraction of heavy elements in the gas that is accreted, and that sets this constant value here. And then the nice thing about the simulation is you can also explore where the metals come from, whether they come from supernova type 2 or supernova type 1a. So this is shown here. You can also make, again, a prediction that the contributions cross essentially at a redshift of around 2.5 or so. So all this are hopefully things that maybe at some point can be measured. Good. Okay, so that was the last thing I want to show about IllustrisTNG. And now for the last 10 minutes, or maybe 12 minutes, I will try to openly say where the issues are. So since this is recorded, I cannot be very openly, but I will try to be as open as possible. So the simulation is, of course, not perfect, right? So it has a lot of issues in terms of how the physics is actually modeled. So one issue is, for example, it depends, obviously, as all these simulations, on certain sub-resolution assumptions. And one sub-resolution assumption in this Illustris and also IllustrisTNG simulation is that the ISM, the interstellar medium, is modeled in a very coarse way using a rather old and, well, I wouldn't say outdated, but rather old ISM model, where the ISM is just treated as a uniform medium. We cannot resolve a hot phase, we cannot resolve a cold phase, and we cannot resolve a warm phase. This has largely to do with resolution requirements and the way how we construct a sub-resolution model, which we want to be numerically converged. Yeah. So the question is, can we go beyond this? And this is something we have been working on at MIT for a couple of years now, and I just want to show, this is unfortunately not yet published, but hopefully we get this out soon. So what we did is we got rid of this effective equation of state and allowed for the development of a truly multi-phase medium, but still constructed the model in a way that it's numerically well posed and numerically converged. Yeah, so what you see here is an isolated galaxy. This is not cosmological, it's just an isolated galaxy which is evolved from early times on until late times. This is the density field, and you see here these hot pockets, or these low density pockets here. This is actually where stellar feedback blows hot phases into the ISM. Yeah, so, and here you see this, the whole thing edge on. You see also some outflows which are triggered by the stellar feedback in these disks. Now you can look at this a bit more quantitatively, and unfortunately this is a rather busy slide, but I just briefly want to mention this. You can look, for example, at the star formation rate, which is of the order of 2, 1, 3 solar masses averaged, which is kind of, you know, for that galaxy type, the right value. So it can properly self-regulate. For example, if you compare this to a model which has no feedback, you get this black line. So you get far too much star formation rate. At the same time, the so-called beta parameter, that's the mass loading. So that's how efficient you can essentially drive outflow. So for Milky Way galaxies, we expect something of the order of, 0.8, 9, 1. And you can also see that this, on average, we also get that value more or less right. And then the most important thing is here, that which shows the PDF here of the gas in the ISM, which you can split in a hot, warm, and cold phase, that we developed now in this model, a truly multi-phase model. Yeah. And just to finish this up, you can also then run cosmological simulations at the same resolution as Illustris or IllustrisTNG. So these are just some first attempts. Unfortunately, none of them is yet at Redshift 0, but just the stellar distribution or the stellar light that evolves. And you can see, you can still create these nice galaxies with all the nice features, but at the same time, you have now a fully resolved ISM where you can study things in more detail, right? Which we could not do before, right? Because we had this simplistic ISM. So it has more predictive power because it can go to smaller scales in the ISM, essentially. Yeah.
Looks like these have surprisingly large bulges for Z1.5. Have you been able to compare this to anything from Canada?
No, we haven't yet. I should also say it's too large. We haven't yet compared, and there's also a caveat on this that there were some changes in this model, so those were run a half year ago, so we currently rerun them, so I don't have the most recent ones. But we don't know, it might be there is an issue, right? But so far, the things we ran looked okay, but yeah, we have to wait for the new runs based on the latest model incorporation to see what actually happens here. But yeah, I agree, we should check this. Okay, so that's one thing I wanted to mention briefly, and then there's another thing that's also never modeled in any of these simulations, which is actually cosmic dust. So if you read the simulation literature, there's literally, I think there are now maybe 2 or 3 papers that ever talked about coupling dust to galaxy formation. And it's typically not done because dust in the ISM makes only 1%, so it's of the mass budget, so it's never considered so interesting. However, it interacts physically with all kind of other processes in the ISM, and also it's, as you know, very important for extinction and attenuation. So we really want to have a dust model self-consistently coupled to the simulation to make all kind of dust predictions also. And this is something that we have also been working on. So this is just, I don't have to motivate dust here. It's just very important. And there's currently no model. So what we did is we implemented this model on top of the IllustrisTNG model. So that's a schematic view of a kind of the first self-consistent dust model that is coupled to a galaxy formation model. So there are various things you have to model. You have to model dust-gas interactions, dust-dust interactions, and also dust productions, and so on and so forth. So I don't want to go into the details here, but I just want to show you some results. So one result is this. This is actually the formation of a Milky Way galaxy where for the first time we could track self-consistently the dust formation. So what you see here is the dust density, the gas phase metal density, and then the dust-to-metal ratio as it evolves as a function of time. Yeah, using this self-consistent model of dust physics. Yeah. So there's no post-processing. It's directly predicted from the simulation, all these quantities. Yeah. And once you have that, you can then, that's the nice thing, you can then, again, see whether this makes sense by, let me just skip over this, by comparing to observations. So specifically what's shown here is this is a comparison to Herschel data, I think. You can compare the scaling between dust mass and a gas mass here, so they're pretty tight correlations, to the simulation data. So in gray here is the observational data, and the colored points are some simulations. You can see that they generally lie reasonably well on that correlation. So there are no extreme. Yeah.
Do you assume that the dust and the gas are physically co-spatial, or is that like an output of the simulation?
So there are two models that we have. The most recent model, we do not assume this. But if you look at the stopping time scales of dust in typical ISM gases, rather short. So the drag force is such that they are usually pretty tightly coupled. But the model is constructed in a way that they could in principle move away, but the code constantly calculates the drag force, and the drag force is usually very large, so that if the gas moves, the dust quickly follows for ISM conditions. Yeah. So. Yeah.
I mean, you're simulating individual galaxies here, so what's the motivation for picking ones that are going to have much higher gas and dust ratios than the observations?
That was just a coincidence, because when we set the project out, we were mainly interested in the dust content of, Milky Way-like galaxies. So we had a sample of Milky Way-like galaxies, and then we wanted to still compare to this correlation trend of the overall sample. So it's just that we don't have at the moment any simulations at lower masses, zoom-in simulations at least. It just started because we were specifically interested in the dust content of Milky Way galaxies. So we put these Milky Way galaxies just on this scaling relation. Yeah.
But there's a parameter which is probably the metallicity that changes that affects the scatter around. So
no,
the gas to dust ratio should depend.
No, not at that dust mass. Not at that dust mass. That should be also where.
You mean in the observations or in the model? Yeah.
Well, the observations that are ranging metallicity, right? So I would think that the gas to dust ratio depends on the metallicity.
No, at that dust mass they don't.
At that dust mass, they
Yeah,
don't.
they do not.
Okay.
They are all those. Anything above 7 is going to be solar.
Okay.
Yeah. I haven't thought too much about it, but this was just a quick check, essentially. But in this paper, there are a bunch of other more stringent tests for the actual dust model. But this one, just was very convincing because it shows the same slope, essentially, and more or less the right scatter. Okay, and then another thing you can predict is also that the dust, for example, in simulations, what's often done is that the dust is modeled just as with a linear relation to the metals. Just have a constant factor, the dust-to-metal ratio. Just multiply this, and then you say, okay, this is how the dust is distributed. But what you see here is if you do this self-consistently, you can look at the fluctuations in the ISM of the dust-to-metal ratio. It can fluctuate by factors 5 or 10, right? So there can be severe fluctuations. So I just caution always when people use the metals as an exact tracer of the dust. It can be a rather bad tracer in some environments. Okay, then you can do the same on large scales. This is some more recent work. You can also predict the large-scale dust distribution. I don't want to go into much detail here. And then you can also look at this is also more recent, into a dust mass function and compare this to data. Black is a dust mass function from data, and these lines, the blue line is a high-resolution simulation. The other simulations are just lower resolution. I can again see that at least that redshift works reasonably well. Good, and then in the last 2 minutes, just the very last thing, another very important thing that all these large-scale simulations are missing, at least all those that are run to redshift 0, is radiation. Yeah, so none of these simulations model radiation. Now again, you can think that, well, maybe that's not so important. And in fact, what most of these simulations do, they assume a uniform, especially uniform time-dependent UV background. just some Hadamardau-like UV background. But if you think about it, then of course near a galaxy the UV field should be very different than in a void, for example, right? So ideally you want to model this radiation field self-consistently because it has an impact on star formation, it has an impact on the cooling and all these other processes. So and especially also if you want to model the reionization, you need some radiative transfer. So what we also recently did is we developed this code is called AREPO RT for lack of a better name, which is a kind of a fully developed radiation hydrodynamics code for AREPO. So AREPO is the underlying code that was used for Illustris and IllustrisTNG. So what you can do now, in principle, you can turn on self-consistent radiation and run the whole Illustris or IllustrisTNG simulation again with radiation. So that has some advantages because you can then also model new effects which we could not model before. For example, this effect, which is a so-called levitation test. What you see here is a test simulation where we have a infrared radiation source at the bottom of boxes here. So this is a box, and then you have dust inside of this box, and the radiation drives the dust upwards, and the dust is coupled to the gas. You can drive essentially outflow. This is a typical example of kind of radiation pressure. And you can let me skip over that. You can also apply this then in a more realistic setup. So you can, for example, say what happens if there's dust around the AGN, and then you have UV and IR radiation coming there, and does this dust then also drive outflow from the AGN? And you can model this, and unfortunately this is also not yet published, but hopefully we also get this out soon. You can then model the jet driving essentially due to radiation pressure. So this is very different from the models that are currently used in these large-scale hydro simulations. So again, you could go beyond the simple models and replace the simple models with something more realistic or something different, a different feedback mechanism. So this is a purely radiation driven in that case. Okay, then let me come to my conclusions. So I think the main takeaway is that a lot of these large-scale simulations can now reproduce many features of the galaxy population very well. This is not only true for Illustris and IllustrisTNG, also Eagle, Horizon, and many of the other simulations can do this now. However, all of these simulations have, of course, the caveat that they have to heavily rely on these sub-resolution models. And there's not a single simulation that has not to rely on them. And the trick is then always how to construct your sub-resolution models and how to make sure that they are both physically, well constructed and numerically well constructed. And this is where the different groups do things differently and where the models deviate from each other. And this challenge will also not go away. It will still be there in 10, 20, 50 years because the resolution or the dynamical range gap between 100 or 200 megaparsec box and the physics that goes on near the accretion disk for a black hole, for example, will always be enormous, and we will not be able to cope with this anytime soon, right? And this is only talking about the dynamical range problem. Of course, there's also the problem if you talk about, for example, star formation. How does star formation itself even work in detail? We even don't know this in all detail yet, right? So there's both physics problems and also numerical problems how to do this. So we will always have to live with this kind of sub-resolution models. And at the end of the day, sub-resolution models, what is that? Well, that at the end of the day is just an effective model, right? So I always tend to make this example. If you want to describe the air in this room, you don't solve the Lagrangian field for the atoms, or you don't do a QCD calculation to describe this. You use an effective model. So the same is what we do in these simulations. It's just effective models. I just think that the name sub-resolution or subgrid models has a bit of a bad connotation, and a lot of people think have weird opinions on it, but it's what we do in all fields of physics. And in fact, these simulations are very close to what people also do in climate research. You have to have sub-resolution models. You cannot model every detail. But you have to make sure that you gauge those models in a reasonable way and that you test them as much as you can. And this is why we want to have this predictive theory, and we can then compare to a large plethora of observational data. And this is why we also need this enormous input from the observers, because we want to compare. And the current frontier in terms of comparing simulations to observations is not so much the galaxy itself anymore. So people are, especially the theorists, are now very interested in the gas around the galaxies. What's going on in the CGM, what's going on in the ICM, what is the phase structure of the CGM, what's the phase structure of the ICM, because all these feedback processes that I just described, they are constructed in a way to regulate the stellar mass, but the way how they do it, they drive out gas or they drive out energy or momentum into the gas around the galaxies, and that can only be constrained if observers tell us in detail what the structure of that gas is. Yeah, so that becomes more and more important that we need input on that side, because different driving mechanisms for these supernova-driven winds, for example, leave different imprints in the CGM, for example. Whether it's cosmic ray driven or thermally driven or whatever, it will all lead to a different imprint. So the only way to distinguish, to really understand what nature does is if observers tell us what the phase structure of the gas actually is around the galaxies. So that would be one important ingredient. Okay, and then I also mentioned that IllustrisTNG is an updated model of Illustris, and the main change is again this AGN model. And going beyond all this, I think there are a couple of new interesting developments. People are working a lot on better ISM models, so we are not the only group. There's also Phil Hopkins and the FIRE collaboration who have done a lot of work on that over the last couple of years, so there's a lot of development going on there, developing better ISM models. Then radiation is a very hot topic now, especially if you go at, if you get closer to the epoch of reionization, if you want to study this in detail. And there it's also interesting if you look at most of the reionization calculations and simulations, most of these simulations stop at a rather high redshift, because that's the only redshift these simulations care about. But then I would even say that all of the existing epoch of reionization calculations cannot be sure that the galaxy population at redshift 0 is correct, because none of these models were ever run to redshift 0. So you then have to live with the fact that you believe something that you only evolved to redshift 5, where we have obviously not as much observational data as at redshift 0, because you don't run it to redshift 0. So this is why it's so important to run these simulations down to redshift 0, because we have most data at redshift 0 and close to redshift 0. So what we want to do with this radiation then is also use the Illustris model or the IllustrisTNG model, where we know it works well at redshift 0, and then just run the whole simulation again with radiation. Only then you can be sure that the predictions you make at high redshift are at least reasonably feasible, because we know that the low redshift population looks kind of okay. Okay, and then another interesting frontier is this dust physics. And in fact, when we started working on dust physics, there was literally no paper looking at this at all. So now a couple of groups are also working on that, and it's especially interesting for the higher redshift regimes. Yeah? So how do dust to metal ratios evolve as a function of redshift? There's not much known. I just had a discussion about this before, and all these kind of. And then how do dust-rich quasars form and all these kind of questions? So there's very little known. And also, once you have a good model for dust, you can also connect it to the ISM model to describe the physics of the ISM better, right? Like H2 formation and many of these things that crucially depend on dust. Yeah, so I think that's also an interesting frontier where some people start working on. And I think I will stop here and thank you. Thanks.
So questions? I don't know. Allison.
So with your simulation, are you able to say anything about the relative importance of different quenching processes that we might look for? Like, for example, like environmental quenching versus quenching potentially from feedback from an AGN, or so-called mass quenching. Can you shed light on that?
You can, because what we record, we know for each galaxy, speaking about the AGN feedback, for example, we know how much AGN feedback went into that galaxy, how much feedback energy went in. So you can do it. I don't think, at least at the most recent simulations, that anybody has looked in detail into that, but you can disentangle it. There was a paper by, I think, Rainer Weinberger a couple of months ago, where he looked at the importance of AGN feedback. That goes a bit in that direction. And there he looked also at the effects mergers versus AGN feedback, I think. So that would be one reference. You can do it, because we have, of course, the detailed merger trees, and we have the environment. And I had a plot there's a plot in the 2014 paper from Illustris, reproducing the Peng et al. SDSS result from 2010, the red fraction as a function of mass and as a function of environment. And you can, in fact, the contours are kind of similar to the SDSS prediction. So you can really reproduce both trends, and so I think you could also then dig out what is more important for which environment and which mass scale. Yeah. So, but yeah, Rainer looked at this a bit in IllustrisTNG. So I I don't have a full overview of all the Illustris paper, whether anybody else looked into that there, but yeah, you can do this. Yeah, Reiner's paper would be a good reference to have a first look. Yeah.
Yeah, great. On a similar note about the environmental quenching.
Mm-hmm.
So, I mean, in the Nelson plot you showed that showed the color distribution, there was a large overproduction. I'm trying to remember the sense of it, where there's an overproduction in Illustris of red things or blue things in low masses.
Let me just go back to the plot.
I'm trying to think about how this relates to kind of the overquenching problem that satellites in dense environments have traditionally been. Yeah, that one right there. So here it looks like Illustris, the original Illustris, had too many, even low mass, too few quenched galaxies at low mass. So that the rightmost peak at low masses is under-predicting the observation. But we also know that simulations, at least prior to Illustris, were over-predicting the number of quenched satellites in dense environments.
Yeah, I think the thing that we see when you compare here Illustris with IllustrisTNG is mainly an imprint of the different AGN feedback. So specifically, it's less driven by the environment, because the environment physics between the two simulations by construction must be similar because the model was not changed. However, what was dramatically changed is the way how the AGN feedback was done, and especially the mass scale where the AGN feedback becomes very efficient. So the reason why the two distributions the color distributions in this mass bin look so different is because the mass scale where the AGN feedback, the radio mode AGN feedback, becomes very important. It's just different between the two simulations. So in one simulation it's already active here, in the other simulation it's not yet very active. So this is where the color is, because once it's active, it's very efficient to really turn it red and dead, right? So it's mostly, and I think I don't know whether he didn't have the centrals for both populations, but I think it's mostly driven by a large fraction by the centrals that are actually quenched by the AGN feedback. I don't think it's a pure environmental effect.
Have you made a plot of just quench fraction in different environments as a function of stellar mass? And it's a pretty robust observational measure. Do you get satellites quenching the right way in either?
Not for TNG yet. For Illustris we did this, but not. Yeah, I don't. Not yet. Yeah.
Yes, I was wondering how the results, depend on the type and also the amount of dark matter that you assume in the model. There are some strong dependence or weak dependence, especially as we discussed the dust. But if you assume that there is some dark matter also between the galaxies, so how do the results can depend on this?
So for these results that I showed here, which are mostly what we call rather large-scale predictions, I never showed you any plot about the internal structure of the galaxy or so. So all these results are rather independent of the type of dark matter, within current constraints that we have, because the large scales, we have very good observations of the large scale clustering and so on. This plot that I showed here. So if you do something very extreme with dark matter, change it in a very extreme form, like if I look at a hot dark matter model, things the clustering as a function of redshift would look different than from the CDM universe. However, if you look at dark matter candidates that are allowed in the sense from a structure formation point of view, then you would mainly change the internal structure of galaxies. And in fact, if you take a warm dark matter candidate, or if you take fuzzy dark matter, or if you take self-interacting dark matter, or whatever type of dark matter you take, you can change the internal structure of galaxies. Like, for example, there's this famous core cusp problem that, we don't, for some low mass galaxies, observations hint towards a core in galaxies, but the canonical cold dark matter paradigm predicts a cusp, and so alternative models can change this. Yeah, but it's an internal property, and none of that what I really showed is internal. So all these were very average, large-scale statistics. So there's typically not such a huge impact. The same is, it's a bit different probably for alternative gravity theories. So there you can also have some large-scale effect. And this is, for example, why some of these FFR gravity theories are pretty well constrained these days, because we know the large-scale structure reasonably well.
Can you say something about this whole problem of overproduction, plain problem, overproduction of small mass halos, our galaxies? You see galaxies?
Yeah, you see galaxies. Yeah.
Or that is just speculation. That more halos correspond
So yeah, so the problem is if you run a dark matter only simulation, which people have done a lot over the last decades, and if you run a Milky Way halo, for example, which has the 10 to the 12 solar masses, and you count the number of subhalos in that halo, it's much larger than what we see as visible satellites for the Milky Way, which is called the missing satellite problem, which was pointed out by Klippin and Moore and others end of the 90s. Now, if you repeat these calculations with these most recent models for baryonic physics and everything, and if you look at the luminosity function of satellites in Milky Way-like galaxies, you actually find that it nearly perfectly agrees with the observation. So what actually happens is that a lot of the star formation is just prevented either through supernova feedback or through the UV background. It's very efficient in stopping star formation in these systems. So a lot of these dark matter halos, which are in the simulations, they just remain dark, essentially. So yeah. So I think this missing satellite problem, this is, I don't think it's such a big problem anymore. Of course, now we have other problems like the too big to fail problem, the diversity problem, the plane of satellite problem, and depending on with whom you talk, they might be problems or not. But I think most of the people would agree that the missing satellite problem is not really a major problem today anymore, if you take all these baryonic physics into account.
Any more questions? I actually have a question. Kind of vague, I think, but you mentioned that this IllustrisTNG requires something like 250 million CPU hours, and it's running on 20,000 cores, right? There are codes which actually run on 100,000 cores, or 200,000 cores. So definitely the gravity is a problem here. I mean, in terms of parallelization and everything. But do you actually see any way of overcoming that problem?
I'm not an absolute expert on code optimization, so it's true, the gravity is a problem, and another big problem is also, if you push, for example, for higher resolution, is also the dynamic timescales. I think that's in the forward going, that's even the larger problem, right? Because let's first talk about the gravity. I mean, it's 1 over r squared, everything talks with everything. So the main problem then in parallelization is that every part in the simulation volume has to constantly talk to every part in the simulation volume, because it's not like a Lennard-Jones potential or so that you have, which is just drops quickly. It's just a 1 over r squared. So every piece of matter, and that is the main challenge, how you distribute then the work properly. Now, there are different ways to do this, like we do a 3-particle mesh method, which is very efficient, and you can also come up with very efficient domain decomposition methods to keep the workload and the memory load feasible. But so I think that is all possible, and we could probably also run this on 40,000 cores, right? If the machine would be, this is more machine limitation. So the strong scaling of the code, especially if it's dark matter only, would still be fine with 40,000 cores, I'm pretty sure. But the main problem really comes if we in the future push to higher resolution, then the timescales that you have to resolve, and there's no way around, the timescales on smaller spatial scales will be smaller than on large scales. That will become an issue, because then, I mean, imagine you have to evolve a void which is very low density, which has many megaparsecs in size. You have to evolve this, and at the same time you have evolve a 10 or 1 solar mass cell at the center of some galaxy, right? So the dynamical timescale can be rather different. And so there are some ideas, I think, to essentially decouple it, to let some part of the simulation be calculated on, to essentially do not only spatial parallelization, but also time parallelization. So that is the only way out, because you cannot do this. So you only have to make sure that you have to look at causality, that there's no problem with causality. But there are people who did this already who made some first attempts in that direction. And I think if we really push to high resolution, then you have to do this. There's no way, because otherwise the code, if the code works is not time parallelized, then it will always wait until everything is at a sync point, right? If you have some part which just evolves on a ridiculously small timescale, then 99.999% of the volume have to wait for this little part to be finished. So you have to do some time parallelization then as well.
Okay, if no more questions, let's thank our speaker.
Thanks.